Welcome to the deep dive. You sent over this really thought-provoking article this
Oh,
week.
yeah. Which one is that?
Oceans were once green, could change color again. Study. And what immediately grabbed me is, well, that iconic image we all have.
The blue marble.
Exactly, the pale blue dot from space. And yet here are these Japanese researchers making this, really compelling case that for a huge chunk of history, our oceans just weren't blue.
Mm-hmm.
So that's kind of our mission today, right? To dive into this surprising history of ocean color, what made it change, and based on this study, maybe even where it's headed.
It's a great topic. Really challenges that baseline assumption.
Yeah, it's a chance to really shift our perspective on something we just assume is blue.
It truly is a fascinating shift. We see that vast blue and just take it as a constant, don't we?
We do.
But yeah, when you dig into Earth's ancient history, the evidence points to a much more vibrant and changeable past.
Mm.
And potentially future, too.
So the study really highlights the link between the ocean's chemistry and, the very first life.
Exactly. It's this intimate dance between the chemistry and the earliest organisms calling it home.
Okay, so let's get into this green ocean idea. The article keeps mentioning these things. Banded iron formations. Now, I'm no geologist, so what are those exactly? Why are they so important here?
Right. BIFs, they call them.
Mm-hmm.
It's remarkable how rocks can tell stories. They're essentially sedimentary rocks.
Okay.
And they have these really distinct alternating layers. You get these rusty, reddish layers. It's iron oxides sandwiched between layers that are poor in iron, usually chert or silica stuff.
Banded. Okay, I see. Like stripes.
Yeah, like stripes. And the key time they were laid down was way back, Archean and Paleoproterozoic eons. I think roughly 3.8 down to about 1.8 billion years ago.
Wow. That's almost hard to grasp. Such immense time.
It really is.
So paint us a picture. What was Earth like back then when these BIFs were forming?
Okay, so imagine a planet where basically single-celled life was it.
Yeah.
That was the dominant thing, maybe the only thing.
Just microbes.
Pretty much. And mostly in the oceans, the
Like-
continents. Pretty barren, just rock sediment, exposed.
Yeah.
So rain would wash iron off these rocks into the water. Plus, you had loads of volcanic activity on the ocean floor, constantly leaching dissolved iron into the seawater.
Okay, so the oceans were just full of dissolved iron, way more than today.
Seems very likely, yeah. Rich in iron.
Right. But the article also stresses something key. The atmosphere, the oceans back then, hardly any free oxygen gas. Very different from now.
Precisely. The Archean eon, an anaerobic world, free oxygen was super scarce. But, and this is crucial, this was also when the very first organisms evolved that could use sunlight for energy.
Photosynthesis, but without oxygen.
Anaerobic photosynthesis, yeah.
Yeah.
And here's the kicker. A byproduct of this early photosynthesis was oxygen.
Uh-huh. So these tiny little organisms were basically pumping out a gas that was, alien to their own world, changing the whole environment just by living.
Exactly. You got it. They were slowly changing the rules. And this new oxygen, this nascent oxygen, immediately started reacting with all that dissolved iron in the water.
Ah, so that's the connection to the iron.
Yes. Think of it like the whole planet slowly rusting. The oxygen bonds with the iron, pulls it out of solution.
Then it sinks.
It precipitates out, yeah, forming those iron-rich layers in the banded iron formations.
Okay.
And only after pretty much all the dissolved iron in the oceans was, used up, neutralized, only then could oxygen finally start building up as a gas in the atmosphere.
Which led to?
The Great Oxidation Event, a massive turning point, absolutely fundamental for the evolution of, us, complex oxygen-breathing life.
And these BIFs, these banded rocks with their stripes, they're like a diary of that whole process. The iron layers mean low oxygen. The red oxidized layers mean oxygen is appearing.
That's a great way to put it. Yeah, the rock structure itself tells this huge chemical story of the ancient oceans. Now, the study also brings us closer to today. They mention observations near that Japanese volcanic island, Iwo Jima.
Mm-hmm.
What's going on there that's relevant?
Right. So the water around Iwo Jima apparently has this greenish tint.
Greenish.
And
Yeah.
it's linked directly to a specific kind of oxidized iron, Fe3, they call it. And interestingly, blue-green algae seem to love it there. They're thriving.
Blue-green algae, cyanobacteria, technically.
Yeah, the article clarifies they aren't really algae, but these more primitive bacteria.
And going way back to the Archean, their ancestors were apparently doing something pretty wild with iron itself.
This is where it gets really cool. These ancient microbes, maybe alongside others, likely use ferrous iron that's like the less rusted form, Fe3.
Okay.
They use that for photosynthesis instead of water like plants do now.
Wow, using iron instead of water.
Which strongly suggests, that the iron levels in those early oceans must have been incredibly high to even make that strategy work. So if they're using iron, what about pigments? The article mentions chlorophyll, obviously, which is green, but also this other one, phycoerythrobilin, PB.
Right. So photosynthetic organisms need pigments to grab light energy. Chlorophyll's the main one for most plants. Algae.
Mm,
It grabs blue and red light best, reflects green, hence green plants.
standard stuff.
But these cyanobacteria, the blue-green algae, they have extra pigments, including PEB. And PEB is really good at absorbing light right in the green part of the spectrum.
Which chlorophyll doesn't do so well.
Exactly. And this is where the researchers did something clever, didn't they?
Yeah, they genetically tweaked modern blue-green algae to make more PEB, and guess what?
Let me guess. They grew better in green light.
Bingo. Significantly better. Which just strongly implies, right, that having PEB would have been a huge advantage back when the oceans might actually have been greener.
Because of all those iron particles scattering green light.
Makes sense. So while chlorophyll works great in today's white light, PEB might have been key for survival in a green-lit ancient ocean.
It really hints at adaptation to a very different light environment back then. A green ocean.
And it wasn't just the lab work. They also ran computer simulations.
They did. Sophisticated models. And those simulations also backed up the idea that the oxygen from early photosynthesis could have created high enough concentrations of those oxidized iron particles.
To turn the surface waters green. Wow, that's pretty convincing when you put the lab work and the models together.
It really weaves the threads together nicely.
Yeah.
And think about the implications. Searching for life out there on exoplanets.
Oh, right.
If we spot a pale green dot with our telescopes, maybe it's not lifeless. Maybe it's like early Earth.
Full of early photosynthetic life thriving in an iron-rich sea, that completely changes how you'd look for habitable planets.
It gives us a whole new potential biosignature to look for, a different lens, really.
That is genuinely mind-bending. Okay, so this shift from green to blue, the article stresses it wasn't overnight. It was super gradual.
Oh, incredibly gradual. We're talking about the Archean period itself spanning, what, 1.5 billion years?
1.5 billion years. Just, yeah.
So plenty of time for things to change slowly, maybe even oscillate back and forth a bit as the chemistry shifted.
Which could explain why cyanobacteria evolved both chlorophyll and PEB, like hedging their bets.
Exactly. Metabolic flexibility. Chlorophyll works great now in white light. PEB might have been crucial way back when things were perhaps greener. Having both covers the bases across vast geological time.
Okay, amazing picture of the past. But the article didn't stop there. It went into the future ocean colors. Sounded almost sci-fi. Purple, red.
Well, maybe less sci-fi than just applied biochemistry, really. It comes back to that core idea. Ocean color equals chemistry plus life.
Right.
So take purple oceans. The idea there is, what if ocean sulfur levels went way up and oxygen levels dropped? Maybe from intense volcanism, for instance.
Okay, high sulfur, low oxygen.
That kind of environment could really favor certain microbes called purple sulfur bacteria.
Purple bacteria, what makes them purple?
They use different pigments, bacteria chlorophylls. These absorb light differently than plant chlorophyll, often reflecting away more in the purpler range.
Ah, okay.
So if conditions were right, these purple bacteria could potentially dominate, outcompeting others, and actually tint the surface waters purple.
Wild. A purple ocean. And what about red? There are a couple of ideas there too.
Yeah, one path to red oceans could be major climate change, like really intense tropical weathering.
More erosion.
Exactly. Washing tons of red, oxidized iron off the land into the sea. Another way is through algae blooms, red tides.
We hear about those sometimes.
Right. If certain red pigmented algae bloom massively, maybe due to nutrient pollution like sewage or farm runoff, they can definitely color the water red locally. The article speculates about scenarios where this could be more widespread.
Okay, that makes sense. We see glimpses of that now. And then way, way down the line, our sun changes things too.
Yeah, long-term astrophysics comes in as the sun ages, it gets brighter, hotter, pumps out more UV light.
Not good for surface life.
Potentially stressful, yeah. Could increase evaporation, might hurt the phytoplankton, the base of the marine food web. The article suggests maybe those purple sulfur bacteria, which often like deeper, lower oxygen water anyway, could gain an advantage.
Or the surface might get less blue-green, maybe more purple, brown, greenish hues, depending on who thrives.
That's the kind of shift they speculate about, yeah. As phytoplankton communities change in response to that long-term solar revolution.
And eventually, the oceans just
Very,
yes.
very long-term,
Yeah.
yes. As the sun expands towards its red giant phase, Earth will get too hot, and the oceans will eventually evaporate completely. But that's billions of years away.
Puts it all in perspective, doesn't it? These potential color changes are just steps along an incredibly long journey.
Absolutely. Thinking in geological time, nothing is truly static. The color of the sea, something so iconic and seemingly fixed, it's actually dynamic. It's constantly shaped by this deep interplay of chemistry and life.
So the big takeaway really is that ocean color isn't just pretty, it's a readout, a reflection of these fundamental planetary processes.
Precisely.
Processes that have changed dramatically over billions of years and, could keep changing in ways we can only begin to imagine. We've gone from maybe green through our familiar blue and maybe towards purple or red futures.
It's a powerful reminder of how alive and evolving the planet is.
Yeah. And it really makes you think what else that seems totally stable and constant about our world actually has this hidden dynamic history or a surprising future waiting.
Exactly. What other constants are actually just snapshots in time, shaped by these huge forces of chemistry and biology? It's definitely something fascinating to mull over.